In the last module, we have discussed about the definition of topological spaces and we have given some examples of topological spaces. But when we have seen the elementary real analysis, we have seen the notion of open set does not require always. In fact, just it is sufficient to know about open interval to give the proper framework of continuous functions. In topological spaces, these open sets will be called bases. So, in this module, we will discuss about bases. In elementary real analysis, we have observed two basic properties of open intervals, that number 1, any real number is contained in some open interval. Number 2, if two open interval intersects non-trivially, then their intersection is an open interval. Keeping these in mind, we give the definition of basis in arbitrary on an arbitrary set. Definition: let X be a non-empty set and a collection script B be a collection of subsets of X, then script B will be called a basis if it satisfies the following two properties. Number 1, for each X belongs to X, there exists some B belongs to script B such that X belongs to B. Second condition, let B1, B2 belongs to script B such that X belongs to B1 intersection B2, then there exists some another B3 belongs to script B such that X belongs to B3 is contained in B1 intersection B2. If script B satisfy these two conditions, then we will say that script B is a base for some topology on X. So, now this is the question, that how a basis generates a topology. That means how using basis we can define open sets. So, let X be a non-empty set and script B be a basis on X, then we declare a set O as open set in X if for each X belongs to O, there exists some basis element B such that X belongs to B is contained in O. We claim that these collections of sets will be a topology on the set X, which we have to prove, and we will denote this topology as tau of B, and we will call that tau B is generated by the basis B. So, theorem. Now, let X be a non-empty set and script be a basis on X. Let tau B be the collection defined as above, that is, U belongs to tau B if for each X belongs to U, there exists some B belongs to script B with the property that X belongs to B is contained in U. Then tau B is a topology on X. To prove this, what we have to do? First, we have to prove that empty set belongs to tau B. This holds vacuously. Whole set X belongs to tau B. This holds obviously. Now, we have to prove the finite intersection property and arbitrary union. Both of these holds, which are easy to prove. Most common example of basis in R, that is in the usual topology, is first one is the collection of all open intervals. We can easily observe that this is a basis. We also get a countable basis of the usual topology of R. In this way, the set of all open intervals with rational endpoints. Next, let us come to the following lemma. Let X be a set and script B be a basis on X, then tau B, the topology generated by B, equals the collection of all unions of elements of B. That means tau B is the collection of all possible union of members of script B. Proof. Since tau B is a topology generated by B, all possible union of members of script B is a subset of tau B. Conversely, given U belongs to tau B, choose some element x belongs to U. Then we can choose an element Bx of script B such that x belongs to Bx is a subset of U. Then U is equal to union of Bx such that x belongs to B. So, U is union of some members of B. This proves the theorem. Let us make an observation that the above theorem shows that a topology on a set is all possible unions of members of basis. Let us come to some characteristic properties of basis. In the above theorem, we mentioned how to form a topology from a basis. The following is one way of obtaining a basis from a given topology. We shall use it frequently. Proposition. Let script B be a collection of open sets of a topological spaces X, satisfying that for each open set U of X and each X in U, there is an element B in script B such that X belongs to script B is contained in U. Then script B is a basis for the given topological space X. So, proof. For the first condition is obvious. For the second condition, suppose B1 and B2 are elements of script B and X belongs to B1 intersection B2. Since B1 intersection B2 is an open set, there exists some B3 belongs to script B such that X belongs to B3 is contained B1 intersection B2. The topology generated by script B is equal to the topology of X is left as an exercise. Now, we will say about when base determines topology. We have already observed that these two are basis of the usual topology of R. But when topologies are given by basis, it is useful to have a criterion in terms of the basis for determining whether one topology is finer than another. That is, if two topologies are given by two bases, is it possible to determine on the basis that one topology is finer than another? We can see this in the following proposition. Let script B and B1 be two bases for topology tau 1 and tau 2 on a set X. Then the following conditions are equivalent. Number 1, tau 2 is finer than tau 1. Number 2, for each X belongs to capital X and each basis element B belongs to script B containing X, there is a basis element B2 belongs to script B2 such that X belongs to B2 subset of B1. Proof. 1 imply 2. Given an element U of tau 1, we wish to show that U is in tau 2 also. That means we have to show that each element X belongs to U, there exists a basis element from the basis B1 containing that point and contained in U. So, let us consider X belongs to U. Since B1 generates tau 1, then there is an element B belongs to script B such that X belongs to B subset of U. Condition 2 tells us that there exists another element B2 belongs to script B2 such that x belongs to B2 is contained in B1, then x belongs to B2 is subset of U. So, U is in tau 2 by definition. Now, 2 imply 1. We are given x belongs to x and B belongs to cube B with x belongs to B. Now, B belongs to tau 1 by definition and tau 1 is contained in tau 2. By condition 1, therefore, B belongs to tau 2. Since tau 2 is generated by script B2, there is an element B2 belongs to script B2 such that x belongs to B2 subset of B1. This property, this proposition has a nice application. First application, that one of the most beautiful example of the above theorem is that these two bases generate same topology. First basis is set of all open intervals and second one is set of all open intervals with rational endpoints. We can observe that if we take some open intervals and x belongs to that open interval, then there exists an open interval with rational endpoint containing that point and contained in that open interval. And conversely, if we take an open interval with rational endpoints and x belongs to that open interval, then the converse holds. So, what is the curse of this property? That is, the Q is dense in R. So, these two bases generate same topology on R. Another beautiful application of the above theorem is that open rectangles in R2 and open disks in R2 generate same topology in R2. We were talking about that how basis determines topology. In the case of R2, we observed that both open disks and open rectangles both are basis for the topology of R2. But how these two bases generate same topology? Because if we take an open disk and take a point in that open disk, then we can put a open rectangle containing that point and contained in that open disk. And also, if we take an open rectangle and a point in that open rectangle, we can insert an open disk within that open rectangle containing that point. That means, by the above theorem, both open disk and open rectangle generate same topology on R2. Similarly, we can say that open triangles or open polygons all generates same topology on R2. Next, we will present a very important example of topological space called Sorgenfrey line. It will be determined by its basis. Here, when we will mention semi-open interval, we will consider this as left closed, right open. Now, consider the collection squared B of all semi-open intervals of sets of R. That means left closed, right open. Then it can be proved that it is a basis for some topology on R. In fact, for any R belongs to R, R belongs to the semi-open interval R to R plus 1. Now, if AB and CD be two members of squared B, that means two semi-open intervals, and R belongs to AB intersection CD, then clearly their intersection is in squared B. So, squared B is a basis for some topology on R. This topology is called Sargent-Frey topology, and with this topology R is called Sargent-Frey line, generally denoted by RL. This topology also called lower limit topology on R. In the same way, taking semi-open interval as left open right close, we can define upper limit topology, but we will restrict ourselves with the lower limit topology. Some important properties of Sargent-Frey line. We have observed that, in fact, from real analysis, elementary real analysis, we know that no open interval is closed in R, but in Sargent-Frey line we will observe that every basic open set is also closed in the Sargent-Frey line topology, that is in the lower limit topology. For this, let X does not belongs to a semi-open interval, consider it as AB. Then it can be easily proved that X is not a limit point of the semi-open interval AB, because as X does not belongs to the semi-open interval AB, that means either X strictly less than B or X strictly greater than B. If X strictly less than A, then we can find a real number R lying strictly in between X and A. Then X to R is a semi-open interval which misses the semi-open interval AB. Now, if X greater than skewed B, then X to X plus 1 is a semi-open interval which misses the semi-open interval AB. That means semi-open interval AB is closed as well in the lower limit topology. We can also prove that every open interval in the lower limit topology is also open. That means the usual topology of R is contained in the lower limit topology. Let us mention another important observation. We have seen that all open intervals with rational endpoints gives the usual topology on R. That means the topology is generated by the open intervals. Now, student can examine what happens if we take semi-open intervals with rational endpoints. Here, it obviously a basis on R, but I will suggest the student to examine that this does not generate the lower limit topology on R. Next, we will give another example which is called K topology. This will be basically required when we will teach, but now we give the example. So, let K is equal to 1 by n such that n belongs to n, this set, and consider the following set AB minus K, that is all x belongs to open interval AB such that x not equal to n 1 by n for any integer n belongs to n. Now, we consider the collections of all open intervals with all sets of the form AB minus K, K. Then it can be examined that this is a basis for some topology on R. The topology it generates is known as K topology on R. Clearly, K topology is finer than usual topology. Note that there is no neighborhood of 0 in the usual topology which is contained in the open interval minus 1 1 minus k, which belongs to the basis considered here. This shows that usual topology is not finer than k topology. The same argument shows that lower limit topology is not finer than k topology. Consider next the neighborhood 2 3 of 2 in the lower limit topology. Then there is no neighborhood of 2 in the k topology which is contained in the semi-open interval 2 3. Thus, we can conclude that k topology and lower limit topology are not comparable, that is, none is contained in another. Next, we give an example called ordered topology. So, how we will give this example? For first, we have to define some order relation on X, on a non-empty set X. Let X be a non-empty set X and let less or equal to be a relation on X which satisfies the following properties. Number 1, X less or equal to X, that is reflexive property. Number 2, X less or equal to Y and Y less or equal to Z implies X less or equal to Z, that is transitive property. Number 3, X less or equal to Y and Y less or equal to X implies X is equal to Y. This relation is called partially ordered relation on a set, and with this relation a set X is called partially ordered set. A partially ordered set will be called linearly ordered if any two elements are related. That means, given any two elements X and Y in capital X, either X less or equal to Y or Y less or equal to X. For example, R is a linearly ordered set, Z is a linearly ordered set, Q is a linearly ordered set. All these are under usual ordering relation of R. Now, let us define open interval in a partially ordered set as in this way. Say, let A B belongs to X. Let us define an open interval AB be equal to all points X belongs to capital X such that X less or equal to B greater or equal to A, where X neither equal to A nor equal to B. Now, if we take the collection of all open intervals in a linearly ordered set, then the collection of all open intervals becomes a basis on that linearly ordered set, and student can prove that every linearly ordered set with this basis is a Hausdorff topological space. Next, we will say some local properties of basis. Definition: by a neighborhood of a point X in a topological space X, we will mean a set A containing X such that there exists some open set O containing X which is containing A. That means, in that case, if A is a neighborhood of X, then X is an interior point of A. We can prove the following theorem for the local property. Proposition: the neighborhood system AX at X in a topological space X has the following properties, where neighborhood system means the collection of all neighborhoods of a point X. First one is AX is non-empty for all X belongs to X. Number 2, if A belongs to AX, then X belongs to A. Number 3, if A1 A2 belongs to AX, then A1 intersection A2 belongs to script AX. Number 4, if A belongs to script AX, then there is a B belongs to script X such that A belongs to AY for each Y belongs to B. Number 5, if A belongs to script AX and A subset of B, then B belongs to script AX. O subset of X is open if and only if O contains a neighborhood of each of its points. That means each of points of O is an interior point of O. I am omitting the proof of this theorem because this is very much easy. An example of this property, consider the set of all open balls in a metric space. So let X be a point in a metric space X and consider the open balls be X 1 by n such that n belongs to n. Then we can say that, we can observe that the collection B A, 1 by n such that n belongs to n is a local basis at X. Next, we will give a extremely important example of basis. Using this, we can give a topological proof of the famous fact that set of prime numbers is infinite. Let us first consider, for A belongs to Z and K being a positive integer, let us define A plus Kz be the collection of all those points A plus Kn such that n belongs to Z. We say that a subset capital A subset of Z is open if each point A belongs to capital A, there is a number K belongs to n such that A plus Kn such that n belongs to Z is contained in capital A. In other words, a subset of Z is open if each of its points is contained in some infinite arithmetic progression. Then these sets of this form A plus Kn is open. That means all arithmetic progression form a basis for some topology. Surprisingly, these basic sets are closed also, because the complement of A plus Kz is the union of other arithmetic progression with same difference. Now we will give the proof of the fact that the set of prime numbers is infinite. Proof: since the set I plus d, I plus 2d, continuing this such that I is equal to 1 to d, that means these d number of sets are open and each of them are pairwise disjoint and cover whole n, it follows that each of them is closed also. In particular, for each prime number p, the set p, 2p, 3p, continuing this is a closed sets. Altogether, the sets of the form p, 2p, 3p cover n minus 1. Hence, if the set of prime numbers were finite, then the singleton set 1 would be open. However, it is not a union of arithmetic progression. So, this claims that the set of prime numbers is infinite. Next, we will define subbasis. Subbasis is a collection of a subsets of X such that for each X belongs to X, there exists some element S belongs to that subbasis which contains that point X. That means, if script S is a collection containing subset of X such that union of script X S is equal to x, then S will be a subbasis of x. Now, from a subbasis we can get the basis taking all possible finite intersection. Then taking all possible union we can get basis. Some example of subbasis. In case of R, if we take the rays, that is a to infinity and minus infinity to a, this is a subbasis. Now, you can observe that if we take all possible intersections, then we get all possible open intervals. That means the basis of usual topology of R. With this, we conclude the discussion on basis, which is the main part of our module 2.